lovely notes today. So, induction and flux. Okay. Well, if you haven't found the videos from the past few notes, they should be posted underneath the notes. Like if you're looking at today, this is the notes. Like I post them right here. The sentence will be deleted when I get done with this video. I'm going to post the videos right there. They're also posted on YouTube as a playlist. Just the AP Physics 2 lectures. So hopefully that helps you find them. Okay, induction and flux. So, induced currents. So we know a magnetic field can create, or we know a current can create a magnetic field. But one of the first things that we start off in this class is that if you have a current flowing through a wire, and it's a lot of current, you just happen to have something relatively magnetic by it, it will react to it. So the question was then, can a magnetic field create a current? Now, Michael Faraday experimented with this, and he was the first person to figure this out. And so this was like literally like decades and decades, because it makes sense that if, you know, current creates a magnetic field, how do we get a current from a magnetic field? So if one is possible, it seems only natural that the other should happen. So there was a lot of research on this. And so here, this is a diagram of essentially what Faraday figured out or set up in the first place. And like I said, this took a while for Faraday to figure this out. What he had to do is he took an iron ring, which is magnetic, and he wrapped 2 coils of wire around it. Now that sounds pretty easy to do, except back in Michael Faraday's day, none of the wires were insulated. They were just bare wire. And he doesn't want current to go through this iron ring, so he had to physically, as he wrapped it, he had to insulate the wire as he went. Which it actually took him 10 days, like essentially 2 weeks if you're only working Monday through Friday. It took him about 2 weeks to just wrap the coil around this iron ring. And so what he did is on one coil, he put a current meter, and on the other coil, he had a battery with a switch. He said, okay, so once he got ready, he said, okay. And when he switched it on, what was interesting is that he expected that he just needed a stronger magnetic field, and that's what the whole point of the iron ring was. However, if you just switch it on, just leave it on, like nothing happens. But he noticed that something would happen only when he switched it on and off. Okay, like right when he switched it on, you'd see this needle flick real quick. And then when he switched it off, you'd see the needle flick the other way. Because the only way to get a current induced in the second coil is if the magnetic field is changing or alternating with time. And so if you turn it on and off real quickly, then you can get an alternating current on that side as well. And so Michael Faraday is the first person to figure this out. Okay. Faraday's experiment did not generate a steady current, however. But again, the instant he closed, we saw a brief pulse of current. So again, he realized it had to be changing. So then he set up a whole series of experiments to test this hypothesis. And so this links to a video down there, which is pretty dang interesting. So here on the next couple of slides, we're going to talk about different things that he tried to induce currents. And so it turns out there's a lot of different things you can do to induce a current. You just have to change the magnetic field. So for instance, if you have this coil of wire connected to your meter here, if you take this magnet and you shove it in, you'll get a pulse of current because this magnetic field is changing. Because if you think about like the magnetic field around like the center coil here, this north pole is going in, and as it's going in, the magnetic field is getting stronger, right? But then if you just leave it there, well, there's no change. But if you pull it out, now you get a current going in the opposite direction. So as you shove this magnet in and out, then you can get an alternating current through the wire. So any sort of magnetic field change can induce a current. Now, how much of a current, for how long, kind of depends on what you're doing. So again, Faraday found that there's a changing current in the coil of wire if and only if the magnetic field passing through the coil is changing. Okay? start thinking about like the second wire. Like, is there any battery hooked up to the second wire? No, but there is something pushing these charges along, and that's where the electromotive force definition comes from, is that it's something pushing these charges along, but you can't say it's a battery, so to speak, because there is no battery. It's just this magnetic field coming from the outside, shoving these charges. So the creation of the electric current by changing magnetic field is an example of electromagnetic induction. So it creates an induced current, and we say that it's induced through the process of electromagnetic induction. So if you hear those fancy terms, electromagnetic induction or whatever, it's just saying that you're making current run through a wire essentially without using a battery or traditional voltage source like a generator or something. So Faraday found that current was induced when the amount of the magnetic field passing through a coil or loop changes. So this is what happens when you slide a wire along a rail, the circuit expands, and so more magnetic field passes through the larger loop. What does that mean? That is magnetic flux. So in other physics classes, we would have talked about flux a couple of different times by now, but we haven't talked about flux in here because it hasn't really come up before. We've been able to ignore it. So let's talk about flux for a second. I can't remember if that's on the next slide. Yes, flux. The term flux is just something passing through an area. Anything. Okay? So in terms of this course, we're going to talk about magnetic field passing through, say, like an area of wire, like a circle of wire. Okay? So the circle will have a certain area, right? We'll calculate the area of the circle. Pi r squared. Right? Or you can calculate the area of a rectangle, so that's an area, and we'll have, in this case, magnetic field passing through it. You could also have the electric field pass through it. That would have a certain flux. Okay? But it doesn't have to be stuff just like that. What I like to say is instead of having magnetic field lines, which are imaginary essentially, or electric field lines passing through it, you can imagine like water passing through this area, or bananas, whatever. It can literally be anything that's passing through this area over time. Okay? And so that's what flux is. So here it gives you a thing about a fan blowing area through a loop. And so if the loop was perpendicular to the fan, you're going to get a lot of air through that. But if you tilt it, a little bit, you're going to get less area, so therefore less flux through the loop simply by turning the loop. And if the loop is perpendicular, well then no air will go through the loop. Okay? And so, again, when we talk about flux, it can literally be anything. And because it can be anything, it depends on what type of flux, or what type of flux you're talking about will give you different units. Because it has to do with an area, something per like meter squared. And so it's like electric field. Electric field is like newtons per coulomb. And so when you do electric field per meter squared, you get like newtons per coulomb meter squared. Or it could be magnetic field through that, which would be Teslas per meter squared. Or if you didn't say bananas over this area, bananas per meter squared. But it's whatever. So the flux can have different units, just depends on what thing is passing through that area. Does that make sense? So I think it's more helpful to visualize something like bananas or water, something you can actually see passing through, or at least with a fan here with air, you can feel it. So here, this is again what I was talking about. So here the loop, we're looking at the side, and if the air is passing through the loop, again, perpendicular is going to get the most air. If it's angled somehow, you're going to get less air, right? And so what we're going to end up having to do is we're going to have to define an area vector, okay, that represents, well, what direction this area is pointing. So to do that, we do the area vector based on the perpendicular surface. So like here, if this was a loop, we would have that area vector coming straight into our floor. So here, again, this is another way we can change the area. So we can change the area by simply turning it, or if the area is physically larger or smaller. Obviously, a larger area is going to field line, so therefore it will have a greater flux. Okay? So this is the front end view, so like in this case, like the air would be coming straight out of this, and again, tipping would cause a reduction in airflow. So here, you can think of it as physically making the loop bigger or smaller, but if you just kind of like turn it, like if this thing is turning towards you, it would make this sort of a shape, like as a 2D projection. Does that make sense? But like if you have it like this and you just kind of turn it, you're going to see less in front of you. So flux, again, this is the definition of it. Flux is the amount of stuff passing through an area. That stuff could be anything. So flux is calculated as stuff times the area it is passing through. So magnetic flux, which is what we're going to be talking about here, is represented by this symbol, capital Greek letter phi, with the lowercase b next to it to indicate it's magnetic flux. And to calculate that, it's going to be B dot A. So it's the dot product, not the cross product. So because magnetic flux should be a scalar, not a vector. So in order to do this, B and A is the area, again, perpendicular to the surface, which we'll probably see on the next slide here. So that would be time, it's B times A times the cosine of the angle between them. Okay. So the cross product is sine, so dot product is cosine. But in the end, there's no direction to the flux. It doesn't matter if it's going left to right, right to left. It's just stuff passing through this area. So like literally, if you looked outside and you defined a loop like around the road, you define the number of cars passing through that area. So we could have magnetic field times the area, we could have electric flux, which would be electric field times the area, or banana flux is bananas times the area, whatever. Okay, so we're going to have flux of anything. You okay with that? And so it's always going to be something times the area through which it's passing through. The dot product, like so. The effective area of the loop is reduced when the loop is tipped. And again, that's where the cosine comes in. So here, when the axis is parallel to the field, we get maximum flux. And if the axis is at some angle, we get less than maximum flux. So again, that's why we use cosine. Because we want them to be parallel. Okay? By parallel, I mean the vector representing the loop, which is perpendicular to the loop itself, and the field line. So you want this, right? You want this angle to be zero. So again, we're going to use probably just BA cosine theta. We don't have any other way of dealing with vectors in here. The SI unit of magnetic flux is the Weber, which is a Tesla meters squared. Doesn't come up that often. What's interesting here is all of these units up here on the wall are like traditional units or units that are using something here. And so what I like to point out is a Jansky. A Jansky is Webers per meter squared times, or divided by Hertz. And so essentially this is like a power almost. This is really energy. Or sorry, it's watts per meter squared, Hertz. But what's funny is that you almost never hear of Janskys outside of almost exclusively like radio astronomy. But what I think is really funny is that like if you watch a movie that has like radio astronomy in it, they'll use the unit of like Janskys and nobody knows what it means because they're just like, what? Because they'll just say it and it's just another thing you think, oh, it's just made up scientific, whatever. But yeah, it's not made up. It is actually a unit they use. So Weber's is just our unit of magnetic flux. I'm probably just going to stick to Tesla meters squared because that's more standard, but just in case somebody throws a Weber at you, there it is. So, which loop has the largest magnetic flux through it? Loop A, loop B, fluxes of the same. Which one's capturing the most stuff for its area? Huh? Not the same. It's really which one has the most dots inside it? Because it's got the most magnetic field lines or whatever this is. Does that make sense?
Yeah.
So like this one would capture 6 bananas, that one up there would only capture requirements are met, now we go to the law part. It says, okay, the direction of the current is such that the induced magnetic field opposes the change of flux. That's it. You go, okay, now that I know that there's a change in flux, the current's going to move in such a direction to oppose or be against that change in flux. I like to call Lenz's law kind of like the teenager's law. That no matter what's happening, the teenager wants to do the opposite. When it's time to get up, your parents come get you up, you're like, no, I want to stay in bed, I don't want to get up. Or your parents tell you it's time to go to bed, but just go play this game a little longer, I don't want to go to bed, it'll be fine. So, like, no matter what it is, whatever the change is, you don't want to do that, okay? And that makes a lot of sense just in terms of, like, the universe. Like, if you roll a ball along the ground, it will slow down and stop because friction opposes the motion. So if you have something moving that's creating a magnetic field, that's pushing things, well, then friction will oppose that and push against it. So imagine you have a magnet coming in. If the south pole is coming towards you, and you don't want that to come towards you, well, then you would show it a south pole, because that would repel the south pole. I'm not going to say it's going to stop it, but it will push against it much more effectively than, say, a north pole. Does that make sense? And so Lenz's law to me makes a lot of sense because it's just like friction. It opposes that motion. It opposes the change. Okay? But here's the deal. Motion is not required to induce a current. Only a changing field is required to induce a current, which is why we talked for so many slides about flux being different by simply the loop being a different orientation. And so there's essentially a few different ways we can get a change of flux. Okay? A lot of them do involve motion, but not all. Okay? So, question 2. The metal loop is being pulled through a uniform magnetic field. Is the magnetic flux through the loop changing? So first of all, we see that there's flux in the loop. Yes? So it's just going through this magnetic field. Is the flux changing? So assuming it's not entering or exiting the field, just staying in there. Yeah, unless it gets out of the field. But you can see here, like if I drag this thing over, it shows the velocity here. I'm going to lose, like you see these 4 field lines here, I'm going to lose those 4. But I'm going to gain these 4. And since they're equal distance from each other, I'll lose those as soon as they gain the other. So there's not going to be any net change in flux. Yeah. Or a very easy thing to do is, like, let's assume that this isn't going on forever, that there's an edge to the field. Like when it's in the field, nothing's going to happen. But as soon as I get this thing to the edge of the field, as soon as I start to lose that, then that would be a change in flux. Because I'll be losing stuff. And so a lot of things that you're going to see, if we have a nice uniform magnetic field like this, we'll have the loop either come in or go out or maybe both. Okay, and that would be a change in flux. But when it's in the field or completely out of the field, no change in flux. Question 3. The metal loop is rotating on a uniform magnetic field. So essentially the same picture, but now we're going to spin this loop. Is the magnetic flux through the loop changing? Yeah. It's going to change because here it's going to get, what, like 16 field lines? But when it's like this, it's going to capture 0, right? When it goes 90 degrees. Then when it goes this way, 180, it'll capture all of them again, and so on and so forth. So this is definitely going to change. So here, this just shows you, okay, like if I have just one loop here, and the magnet's just sitting there, I'm not going to get any current. Okay, so now let's apply Lenz's law. So the first thing is you have to make sure that there's a closed loop. So if being connected to this meter, that makes it a closed loop. And is the flux changing? Well, for part A, it's just sitting there. So is there any flux changing? No. So this area here is going to capture a certain number of field lines, and it's going to stay the same. I think. Okay. So what happens if we move the magnet down? Okay. Well, if we're moving the magnet down, well, the north pole, the field lines are closer together at the pole than they are further away. So as it moves down, it's going to capture more field lines. The magnetic field is going to get stronger as that north pole goes down. So now we can apply Lenz's law. And Lenz's law is all about the direction of the current in the loop. So pointing down through the loop, and it's getting stronger because the North Pole is going down. You with me? Going down, getting stronger. The loop wishes to oppose that change. It's fine with it going down, it just doesn't want it getting stronger. So what the loop will do is it will run the current in whatever direction it needs to induce a magnetic field that's going up. Does that make sense? Because if the North Pole is going down and getting stronger, well, it wants to push the North Pole up to stop that. Okay, now it's always going to be weaker, so it's not really going to stop it, but it's going to try to. Okay? So that's the first key there. It's going down, getting stronger, so this thing is going to induce a current going up to oppose it. So now you go, okay, how do I figure out what direction the current goes? Well, use your right hand. Okay? Because remember, your right hand on a wire, you point your thumb in the direction of the current, your fingers curl in the direction of the magnetic field. So if we're looking at this loop here, we just said we want the induced current to go, or the induced magnetic field to go up. Right? So your fingers need to come up through the center of the loop. So you can imagine you put that loop in your hand, and your fingers need to curl up around it. And so the current should go in the direction of these purple arrows that you see here on the screen. So when you take this magnet and you shove it down, it's going to induce a current in that direction. You all see that? It's going in the direction, your thumb should go in the direction of the purple arrows. Your fingers should go in the direction of the field line.
Isn't it going the other way?
What do you mean?
Isn't there not going the other way of the arrow?
No. The arrows are pointing in the direction a current or a positive charge would go.
So are we pointing the way that the electrons go?
No.
I know what you're saying.
Your thumb points in the direction of a current, which is the direction positive charges would flow. So you grab your pencil with your right hand. Like this, like a wire. Yeah. So that's the wire.
Yeah.
Okay. And so the wire is coming out, going through your hand back around like this. Can you visualize that? So your fingers are going up through the center of the loop.
Yeah.
So the current's going in the direction of that arrow, that purple arrow. So literally what you just did right there is like putting your hand right here.
Okay.
Does that make sense?
Yeah.
Okay?
Mm-hmm.
So that is how we determine the direction of the current, because it will always, the magnetic field will always oppose the change. Okay? Now here's the deal. As that magnet goes into the loop, it's getting stronger. At some point, something has to change. Because if the magnet keeps going, well, it's going to switch from north to south, I suppose, right? Or if it stops, well then it will stop getting stronger. Right? So in that case, if it just stops, well, current will just stop. But if the magnet starts to go, let's say, back out, well, the North Pole is still pointing down, but it's going down and getting weaker. Well, current loop don't want that. Current loop don't want no change. So it's going down and getting weaker because you're pulling it out. Well, now the magnetic field will oppose that change. When it's going down and getting weaker, it's going to try to reinforce that and make it stronger, to pull it back to where it was. And so in that case, the magnetic field will switch on this, and the current will go in the opposite direction. Which is why it generates an AC current. So any change will generate a current, but as soon as that change changes, well, so does the current. Takes a while. So here, in this case now, this is what I just said. Now the magnet's moving up, but again, the field is still going down. So it's going to try to reinforce that field, and you see here you can see the induced field is going down as well. And so that causes the current to go in the opposite direction because you've got it. If you're grabbing it here, your current's going to go the other way. Everybody okay with that? So the thing is this is Lenz's law. Like, this doesn't have any numbers or anything in it. Like, you get the numbers from everything else, okay? But here it's going to be important to know, like, okay, what direction is the current going to go? Because the question will be, like, instead of having a current meter over here, it'll have like a light bulb or some other circuit. Be like, okay, over here, if this is a And so it's usually just a big coil of wire that we have spinning around, or we have a coil that stays stationary to spin a magnet. So as the coil rotates, one edge is always moving upward through the electric field, while the other edge is always moving downward. The motion of the wire induces a current, which is then removed by the brushes that press up against the rotating slip rings, right? Time to take. So this should look very familiar, okay? So here, in this case, if you have a generator, what's not shown in this picture is there's something out here physical that's turning this loop of wire. Does that make sense? So like you're turning it, the wind is turning it, the hydroelectric water is turning it, whatever. Something is turning this coil, okay? And so what happens is, you know, if you've got, let's say, a magnetic field going this way, as this coil turns up, right, as it's going up as it's shown in this picture here, the magnetic field is going to capture more and more magnetic field lines, more flux, right, as it's starting to rotate like this. And so what's going to happen here is that the coil is going to induce a current, and that current is going to have a magnetic field that opposes this change. So as it's rotating here, it's going to capture more magnetic field. So we want to have less magnetic field from the loop. So it's going to oppose that change. So if the normal magnetic field is going from left to right, the induced magnetic field would be going from right to left, which is what's going to cause, like your fingers would go into the loop here, which is what causes the current to flow as shown in the picture. Okay? But when it gets up to the top, that's going to have maximum flux, right? But once it goes over the top, well, now your flux is going to start to decrease, which is going to cause the current to flow in the opposite direction, which is again why you have these, well, the slip rings are here so it doesn't twist up. But in this case, it doesn't have anything to compensate for the difference in induced current, so it just goes back and forth. Like if you just turn this, it just makes an AC current. Because it'll go one way, but again, once it gets up to the top, it's going to start to come down, and then your loop will be capturing less and less magnetic field. So the current will switch directions at that point to oppose that magnetic field change. And it'll keep doing that until you get horizontal where it captures 0, and then it will start to switch back the other way because it's capturing more magnetic field. So like every 90 degrees, this thing will change. Does that make sense? So as the coil generator rotates, the sense of EMF changes, giving a sinusoidal variation of the EMS as a function of time. Alternating sine of voltage produces AC. Magnetic flux can change in 3 ways. So these are the 3 ways you can change your flux. You can change the magnetic field through the loop, which means you can, you know, it's like what we just talked about earlier, it's like you shove that magnetic field in or out. Like literally you can just move the magnet. Right? 2, you can change the loop area or angle, or 3, the loop moves into or out of the magnetic field. Okay? So there's, again, basically 3 different ways to change your magnetic flux. You can change the magnetic field itself somehow. You can change the loop size physically, or to change the angle it's rotating at to capture less flux. Or the loop moves into or out of the magnetic field. Essentially like moving in and out of the magnetic field, to also induce a flux. So again, the induced current generates its own magnetic field, and it's always opposed to that change. So it's key to remember it's opposed to the change, not just opposed to the direction of that external magnetic field. It's opposed to the change, whatever that change is. So that's the first key, is you got to make sure A is closed loop, B, that you have magnetic fields changing. Now that you know it's changing, now you can try to figure out the direction of your current. So changing flux, like turning the crank on a generator flashlight, rotates a coil of wire in a magnetic field of a permanent magnet. With the switch off, there's no current and no drag force, so it's easy to turn the crank. So that's one of the things I plan on showing you today with the demos. I don't have a generator flashlight like that, but I do have a flashlight like this. What's funny is this flashlight is dead, but it's on. This is a magnet. See my magnet right there? This is a coil of wire. The flashlight is on, but it's dead. You'll see that it comes on. Now, if I actually left this off, you can shake this, and it has a little capacitor in there that will build up the charge.
Wait, where is this property?
Oh, it's on the circuit board. But like literally coil wire, bang. So you can change the flux by shaking it, and we can have current go through the wire. It's called a shake light. Now theoretically, if you wanted to like use this at home, the great thing about it is it never really runs out of batteries. Like honestly, if you wanted to charge it, you would turn it off and then shake it again. Does that make sense? But the problem is like when it's dead, it's real hard to tell if it's on or off. So you shake it. Because obviously it uses it, it's just one LED, it's pretty efficient, and it can store up the charge for a while. There you go. You did it, you stored the charge. Okay. So one of the things that's really nice is you can buy like different like little radios or flashlights that have like a crank. The crank handle is a little bit more useful because you can just crank it. You can go a lot faster that way to build the charge. But when you're actually building it up, you can actually feel a physical difference because it's trying to oppose all of these changes that you're pushing it through. So no matter what is happening here, it essentially has like a drag force on it. Question 4. An induced current flows clockwise as the metal bar is pushed to the right. So here we have a loop, right? Like a U shape, and then we have this bar that's closing our loop. So we have a closed conducting area here. And this, it says, okay, you're going to shove this bar to the right, and it induces a current as shown. Okay. The magnetic field points blank. So here we're talking about this external magnetic field that this thing is reacting to. Because again, if there was no external magnetic field, nothing would happen. Okay. So, it'll take a second and then we'll talk. Shake light. What do y'all think? Okay. So chances are, yeah, it's going to be perpendicular to this loop. So probably C or D, just looking at it without thinking too much, is probably a safe bet. Okay. Which again, you have multiple choice. If you can eliminate a few of the answers, hey, you're on the right track. So here, this thing is moving to the right, and this thing has an induced current. So what I would do is say, okay, got my right hand, I'm going to grab this somewhere. So if we imagine I'm grabbing the bottom of the loop here, I'm grabbing it like that, right? So my thumb points to the left, the loop at the bottom loop here. My fingers would curl in to the loop. Everybody with me? So that's what's happening, okay? So if this is the induced current, remember it's going to oppose the change. So what that means is, it could mean two things. It's all about the change here. So in this case, the loop is getting smaller. So whatever is happening in this loop, whatever direction the magnetic field is going, it's getting less of that. So if this thing is pushing in, it's going to be going in the same direction as the field that's going in because it's getting less in, so it wants to reinforce the less in by going in. Does that make sense? So think about it. Like if I had, if you drew like 10 dots inside of this thing, if they're going in and this bar is sliding to the right, it's going to get less of those dots, right? So this thing wants that to not happen. It wants to keep all of those dots. So it's going to put its own stuff in to reinforce the in. And so this should be into the screen. Well, no. If you grab it from the top, your thumb should be pointing up. So your finger should go in down here. Okay? Oops. And the thing is like, if you think this is tough or tricky, it is. It is confusing. Okay? Like there's a reason why, like when we talk about magnetic Transformers use electromagnetic induction to step up or step down voltage. That is why they're called transformers, because they change or transform your voltage. Okay? Okay. That's literally what the word transform means. It transforms your voltage. Here's the deal. Transformers only work with AC, and hopefully you guys can see why. Because transformers essentially are two coils of wire connected essentially kind of like on an iron ring, like we started off when we talked about Faraday. And again, if we had DC, you could only get current running through the other coil if it was switching on or off. But with AC, with a continuous variation, we can continually induce a current in the second coil. Now here's the deal. With transformers, we're really not going to get very deep into them, but essentially the gist is, if the coils both had the same number of turns, like say 5 and 5, what's going to end up happening here is it'll induce a current just like we talked about, but the voltages would remain the same. You would have a reduction in the current flowing through the second wire. Okay, let me take this down. In an ideal situation, if you had the same number of coils, you would end up with the same voltage and the same current on both sides of your transformer. Okay? Perfect world. We don't live in a perfect world. There's always going to be some energy loss, so you're going to lose it typically as the current. And it could be a little bit of loss of voltage, either way. But the way a transformer works is you're going to change the number of coils. So if you start with, say, only 1 or 2 wraps here, and you end with, say, like 100, that would be a step up transformer. It will take the voltage from, say, you come in at 12 volts, and it'll step it up to maybe like 100 volts. It really depends on the ratio of the two coils. Okay? But here's the deal. If I came in with 2 and came out with 200, let's say that steps it up by 100 volts. Okay, that's a step up transformer. So what's a step down transformer? A step down transformer, you come in with 200, go out with 2 volts, and it will step it down. Now that's not exactly what the formula says, but I'm pretty sure we don't cover the formula in here because I can't remember it all. So whether it steps up or steps down just depends on the ratio of the 2 loops. And literally, if you wanted your transformer to do the opposite, you would just turn it around in the circuit. Now for you guys, you can see these pictures of transformers. So in the older neighborhoods, we have the transformers that are up on the poles. They're usually in a light gray or white cylinder like this. And then in newer neighborhoods where the power lines run through the ground, you have these green boxes. Those are transformers. So the way AC works is the power plant generates power, and it has to send it to your house. But long ago, we talked about how a wire has a certain resistance to it, right? It's based on the resistivity, what the material is made out of. But it's also based on the length of the wire, the area of the wire, and how hot or cold it is. But here's the deal. In a circuit, like in a lab or your cell phone, how long are those wires? Almost no length at all for some of them. They don't have any significant length to them. And most of them aren't flowing a significant current, so the area really doesn't matter either. The resistivity matters the most in those, but as long as we make it out of essentially anything metal, then it's pretty much good to go. But when it comes to power coming from your power plant, is there a power plant around the corner here? No. The closest one is actually the Denton Power Generating Station up on Loop 288, and it's not on most of the time. For instance, when you were getting cold in February, that thing was off. So the power that comes to your house or that comes to the school has to travel relatively long distances. And I'm talking like sometimes tens, if not hundreds of miles across the grid. But here's the deal. 10 or 100 miles, that's a significant length to the wire. And so even if we make it out of a relatively conductive material, it's going to have some resistance to it, okay? And so one of the things that we can do is we can increase the area of those wires. And so high voltage power lines tend to be very heavy. What is this? It's copper. It's just a chunk of copper. A power line could be this diameter. Pick that up.
Okay, that's heavy.
Yeah. And that's not a very large section. Yeah, that thing's like 80 pounds. So the whole deal is like, you can imagine these things, I'm not saying they're running all copper wire or whatever, but yeah, you can, you can imagine that these things are heavy,
Yeah.
okay? And like I said, that's just a little cross-sectional area. Yeah. Well, and so, again, that's why they don't typically have insulation on, because it's going to make it even heavier. And the thing is these power line, these towers have to be able to bend and flex with the wind. And so the stronger the wind is doing it, you can imagine the force is larger, and we don't want them to fall over all the time. But here's the thing. The reason why they're up that high is generally the higher the power lines, the higher the voltage, so you get more insulation with the air. Because here's the deal. If they sent power through the lines at like 120 volts, let's just say 100, let's round it off, it costs a certain amount of voltage to overcome a certain amount of resistance, V equals IR. So if you want this current to flow through the wire, because again, the wire would act like a resistor, but like a large resistor that's in series. So the current has to be the same at both ends. Does that make sense? Because it's a series circuit. Current is the same. So when it passes through this resistance, it requires a certain amount of voltage. Well, if it was 1 volt per mile, you say, oh, that's not too bad. But if it's 100 miles away and it's only sending 100 volts, well, it'll have 0 volts at the end of the line. That's not good. So literally, that would represent power as current times voltage. Well, your current wouldn't change, but your voltage would be 0. So that would represent 100% power loss. Not great. But if you send the voltage at not 100 volts, but send it at, say, 100,000 volts, well, V equals IR, the resistance of the wire is the same. So you would still lose 1 volt per mile. That's my made-up thing. So at the end of 100 miles, you would lose 100 volts. But what's 100 minus 100,000? 99,950. So we still have the majority of the voltage left, and the current is the same, and so that represents almost no power loss at all through the lines. And so simply transmitting the voltage, or simply transmitting the current at a higher voltage, decreases our power loss. Does that make sense? Which is why we want high voltage power lines. Because we can transport it long distances and have relatively no power loss. But here's the deal. Do you want 100,000 volts coming out of your wall? No. We want a little less than that, and so we have to transform it with these transformers. So these are the local transformers that are like in your neighborhood, but they're not transforming like, say, 100,000 to just 120. They're transforming more like 1,000 to 120. So how do we transport these things at 100,000 or maybe 1,000,000 volts? How do we step it down? Well, there's what we call power substations, and there's actually one across the street from the school. Like we got like church, graveyard church, and then power substation. Okay, that power substation, like I don't know what voltage is coming in there, but let's say 100,000 volts comes in, maybe only 1,000 volts comes out to go through the power lines into your neighborhoods, and then that gets stepped down again when it's going into your house. And so obviously by the power station, the power plant is going to generate the power at whatever, depends on the power plant, but then they're going to step up the voltage to whatever those lines need before it goes out of the plant. So outside your power plant, you'll have another power substation, but it's going to have transformers wired the opposite way. Does that make sense? So hopefully that gives you an idea, but transformers are everywhere. Because here it points out your cell phone charger. Do you use your cell phone charger? Do you use 120 volts to charge it? I'll give you a hint. If you don't know, most of you can take your cell phone charger, it's got that box on it, but you can also just plug it into your computer. USB, universal serial bus. If you plug something into USB, it gets 5 volts. So your phone charges with 5 volts. Not the 120 comes out of the wall. That's the whole point of those boxes that you plug in, is it transforms the voltage to whatever you want. So for instance, my laptop here doesn't charge at 120 volts. It charges at 240. So I need a transformer to actually step up the voltage here is this can only happen with AC because of the magnetic field has to change in order to induce a current in another coil. And so the key here is that these transformers are connected magnetically, not electronically, which is very interesting, at least to me. And that looks, we're done. Okay. So these are all the steps to do. This is essentially what we've already covered, but this is kind of like on one slide here. So here it says, number one, determine the direction of the applied magnetic field. The field must pass through the loop. Okay, so the first key in order to figure out Lenz's law here is, first of all, make sure A, a closed loop, and B, the field has to pass through the loop, and then figure out the direction of the applied magnetic field, typically, if you're trying to figure out the current produced. Number two, determine how the flux is changing. Is it increasing, decreasing, or staying the same? Staying the same? No current, right? So the first thing to do is figure out, okay, here's my loop, it's going in. Okay, that's step one. And number two, okay, it's going in, but it's getting stronger. Or it's going in, but it's getting weaker. You see that? Or it's going in and nothing's happening. Then three says, determine the direction of the induced magnetic field to oppose the change in the flux. Because once you know the change, let's say it's going in and getting stronger. Well, then the loop will, for increasing flux, the magnetic field points in the opposite direction. It's going in, getting stronger, we don't want that, so it's going to go out. The induced one. Or if it's going in and getting weaker, it doesn't want that, so it's going to go the same direction for decreasing flux. For a steady flux, no magnetic field is going to be induced. And then four, then you determine the direction of the induced current. So now that you know the direction of your opposing magnetic field, then you go, okay, point your fingers in the direction of that induced magnetic field, however you need to, and then your thumb will point in the direction of the current. Again, these are loops, so you have to be careful and specifically think about one part of the loop, okay? Just focus on that and go, okay. Just literally think about, okay, loop is in my hand. How do I have to grab that so my thumb goes in the right direction? All right. So question 5. A bar magnet is pushed towards the center of the wire loop, which is true. There's a clockwise induced current, there's a counterclockwise induced current, there is no induced current. Step one was what? Loop is closed. Okay, so step one, determine the loop is closed and determine the direction of the applied magnetic field. So what's the direction of the applied magnetic field? Up through the center of the loop, right? Then step two says, determine how the flux is changing. So it's going up. Is it going up and getting stronger, or going up and getting weaker, or going up and staying the same? Increases. So it's going up and getting stronger, right? So now step 3. We need to oppose that change. It's going up and getting stronger, so that's increasing. So our induced magnetic field points in the opposite direction. Right? We oppose that change. And now that we know that it's going the opposite direction, we're going to use the right-hand rule to determine the current direction. So it's going up, it's getting stronger. Our thing is going to oppose that. So let's say we grab the front of the loop here. Okay? So this is the front of the loop. If I grab it like this, my fingers will be going up to the center. If I grab it like this, my fingers will be going down to the center. So do I want to go down to the center or up to the center?
Down.
Down, because we want to oppose that change. So that will go like this. Now, if it's clockwise or counterclockwise, it kind of depends on how you look at the loop. Now, if we kind of look at it like this, going around like this, that would be a clockwise induced current, okay? So you have to be kind of careful, especially with these three-dimensional views here, right? So in this case, can you see, you guys see that the arrow is behind the piece in the front there? Okay?
Well, my problem is that, like, if you grab it in the back, where it's going counterclockwise?
No. If you grab it in the back, then your field line still go down, but it's still going to go around like this.
If you're going down, then that's it, that way, right?
Inside, this is going inside the loop. In the back, that's going
Oh, the
inside.
oil will be okay.
Yeah, your fingers have to be in there. Does that make sense?
Easier, yeah.
Okay, yes. Your fingers should be inside in whatever direction you're pointing.
Okay.
to see. I gotta answer my phone.
Hello?
Is Ron the free? No, he's asynchronous. Yes. Thanks. Okay, so for number one, there's no current, right? Good, it's not changing. But like step one is determine this, so in this case, the field will be going down this, there's just no change, okay? So for number two, the magnet is pulled completely out of the coil, okay? Well, in that case, it's going, the North Pole is going this way, and it's getting weaker. So the change is going, or your induced thing is going to oppose that change, so it's going to want to go in the same direction. So now you want to put your fingers inside this tube somewhere. And wherever you do it, your fingers got to go in the tube, because that's the direction, as opposed to coming out of the tube. So we're going to grab, like, say, this end of the tube. So the current, so like if you imagine this loop here on top, the current's going to go up, right, to this little teeny part of the coil. So it's going to go around like this, and then when you wrap it around, the current's going to go this way. You okay with that? You okay with that?
How's current going that way?
Well, okay, so you got this, the current's going up.
Yeah.
Right? So on any of these coils, like right here, this would be going up, 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 right? So if it goes up, then it goes around the back, so it has to go down, and then come up again. And go around the back where it goes down, and then up, down, and up. You see that? Then it goes down, and goes this way. Does that make sense?
Yeah.
Okay. So that should be, well, A, as I've already shown you here. So the current should go from right to left, right? Which is what we just said. Then the bar magnet is completely out of the coil of rest, so nothing. Then when you shove it back in, it should do the opposite, right? Now there's a great FET sim for this, where you can play around with it, and I'll show you after these notes are over. That can really help visualize some of these things. So here, a loop is moved towards a current carrying wire, as shown below. As the wire is moving, there's a clockwise current around the loop. Oh, is there a clockwise current? Counterclockwise current, or no current? So again, we have a current flowing below, right? So you wrap their finger around the current carrying wire below. So it's going to go in a loop like this. So it's going to go into, the magnetic field is going to go into this top loop up here. In here, out of the bottom, right? In, out. So for this particular wire loop here, it's going into the loop, okay? So that's the first thing we had to do, determine the direction of the magnetic field. It's going in. Now, second step is trying to figure out, is it going to get stronger, weaker, or stay the same? Because is this current in the wire changing? No. So we're not getting any magnetic field changes. So the magnetic field is going to stay the same. But what's this yellow loop going to do? It's going to go down. It's not entering the field. It's just going to get to a stronger field because the magnetic field is stronger closer to the wire, right? So in this case, we have the magnetic field going in. Since it's going down, it's going to go in and get stronger. So this thing is going to oppose that, so it's going to come out. So its induced magnetic field is coming out of the board in this case. So now we can grab this loop wherever we want. So if I want it to come out, if I'm saying grabbing this side, is this going to come out? No. So I need to go this way, right? And so again, if I'm down here, this needs to come out, this needs to come out, this needs to come out. So the current's going to go like this. Is that clockwise or counterclockwise? Is that what y'all got? Yeah. All right. Faraday's law. So here's the deal. Lenz's law gave us the direction. This gives us the actual size of the current. Okay. So an induced EMF, epsilon, is the EMF associated with the changing magnetic flux. The direction of the current is determined by Lenz's law, which is what we just spent basically a whole lot doing. The size of the induced EMF is determined by Faraday's law. So another way to this is epsilon equals I times R, which is basically just Ohm's law. Now with me? The V equals IR. But this isn't V, this is specifically talking about this induced current that's going through it. And again, that's why we call it EMF instead of a battery, because like, it's really weird to look at the second loop and go, okay, it's going like this, then if you're trying to apply Ohm's law, you go, oh no. Because Ohm's law is V equals IR, right? And if you just have current flowing through this loop, like literally, it could just be a single loop of water. Is there a battery in that? No. So you're like, where's the voltage pushing this? Well, it's the induced magnetic field that we just talked about. And so just looking at that, you're like, well, there's a current running around in here. How much current? Well, really, it depends on this induced EMF and the resistance of the wire. So, how do we calculate this? So this is how we calculate the induced EMF. So Faraday's law is equal to delta flux, magnetic flux, divided by time. So it's a change, so it's negative. Okay. So Faraday's law is a basic Faraday's law is a basic law of electromagnetic induction. It says the magnitude of the induced EMF is the rate of change of the magnetic flux through the loop. So this might look like a lot, but I think this should make some sense here. So first of all, it's negative, because it's going to be opposed to the change of flux. Are you with me? That's the delta. So you have to have a flux to start with, or maybe you don't. But you have to have a change of flux. So we talked about there's three different ways to change that flux, right? You change the magnetic field strength, you change the area, or you change the angle. But remember, flux is V dot A. So any change in the magnetic field will induce a current, or induce a voltage, right? Any change in the area will induce a voltage, or any change in that angle. So it's V dot A, so it'll be B times A times cosine of the angle between them, right? So any one change of those three things can induce a thing. And it has to, occur over a certain amount of time. So obviously the shorter time that you do that, the higher voltage you can generate, right? So even with a relatively weak magnet, if you just make it go really fast, you can induce some really large currents with that. So, the following figure shows a 10 centimeter diameter loop in three different magnetic fields. The loop's resistance is 0.1 ohms. For each situation, determine the magnitude and direction of the induced current. So magnitude would be Faraday's law, direction would be Lenz's law, okay? So, let's start with M. Here it shows a magnetic field doing what? What's the magnetic field? Increasing, but what direction? It's going out. The dots are out. The second one's in, right? The magnetic field is coming out. So, first of all, is there a flux here? Yes. There's some things going through this loop. And it's increasing with time. So, in terms of the direction, we go, okay. Magnetic field's coming out. It's going through the loop. So it's coming out and it's increasing. So we want to oppose that change. So this thing should have a magnetic field going in. So we grab the loop in such a way that our fingers go inside. So it should be up on this side of the loop, down on this side of the loop. So what is this circle? What direction is this? Clockwise or counterclockwise? Clockwise. Are you okay with that? That's the direction of the induced current. Now if we wanted to calculate the magnitude, we have to go, okay, I equals epsilon over R. R is our resistance, that's 0.1. So to calculate epsilon, we got to do negative delta phi over delta T. But here's the deal. It gives us, this is T per S. This is the magnetic field changing per second. It's 0.5 Teslas per second. So what's happening there is it's already giving us, but remember that phi is V dot A. A cosine theta. So first of all, cosine in this case, what's their angle? Well, they're parallel, so there's no angle, so we don't have to worry about cosine. So it's just B dot, or B times A. Well, B over time is 0.5. So A is just the 10 centimeter diameter, so we have to calculate our area based on that. Okay. So we should be able to do that. We'll save the calculations for a second, but if we go to B, what's the difference here? Well, in this case, the magnetic field is going in, right? But it's these two situations look very different. But because they're both changing by 0.5 Teslas per second, first of all, our induced Emf should be the same, and the direction of it will be the same. Does that make sense? Now, what about that last one? What's the direction of that induced Emf? No, not up. Right? It's zero. There's no loop. No flux through that loop. Because yes, it's changing, the magnetic field is changing, but the loop is 90 degrees, so it's not going to capture anything. It's like holding your basket in the river. If you hold it like with the river, you get a lot, but if you just kind of put it like this, the river will just go around it. It doesn't care. So here, C has 0. For A and B, it leads to the same calculation here. So you can see here that I didn't put the negative sign on this, because the negative sign would indicate a direction for your voltage. And that only makes sense in terms of Lenz's law. So what I would do is just drop that negative sign from Faraday's law and just use this as a magnitude calculation, and then let Lenz's law handle your direction. Okay? So here, the Faraday's law is the change in flux over time. So that comes out to delta VA cosine theta over 2 delta T. But we already determined cosine was 0. Right? Cosine of 0 was 1. So that just gives us B times A. But B over T is the 0.5 Teslas per second. Like B is Tesla, second is time. So we've got that change in time. And then we have to do the area, pi r squared. Okay? And it gives us 0.0039 volts. Not a whole lot of voltage. And then if we calculate the current, well, the current is 0.0039 volts over its resistance. And again, that's not much resistance either, so it leads to a fairly significant current, actually. I mean, that's 40 milliamps. Which, if you could hook your fingers up to this, you would definitely feel it. It only has to be about 1 milliamp for you to feel it. Pretty good. And the direction here is clockwise, which we determined. Put fingers in with clockwise. And then C, there is no current. But A and B are going to be the same. I think it makes sense that they're the same mathematically because, well, the numbers are the same, right? They're both 0.5, they have the same resistance, they have the same diameter. So that stuff should come out the same. But also the direction is them coming out the same, which is not necessarily what you thought.
So what did you say opposite direction?
Not the same direction. That's wrong. Because, I don't know why I said opposite direction. Because we determined that it's the same direction, right?
Yeah.
Because this one's going out but increasing. So it will oppose that by going in. Whereas this one's going in but decreasing, so that will oppose it by also going in. So they should have the same direction. Which is why this just says counterclockwise but not